Draper Laboratory is pleased to participate in the AACUS Concept of Operations Industry Day Workshop. We are excited to partner with others to ensure the broad set of capabilities needed to bring the AACUS technology to fruition. Dr. Draper led the MIT Instrumentation Laboratory in the establishment of inertial navigation technology. In 1973, the Instrumentation Laboratory divested from MIT and became Draper Laboratory. The lab is committed to solving the nation's most challenging technical problems. We do this through leading-edge research and development and a close association with academia, as well as with our sponsors and their real-world problems. We bring novel system concepts through prototyping and demonstration in realistic operational environments to make them ready for production and application. Draper understands the challenges that human-controlled autonomous systems can present. We have been developing autonomous systems as far back as NASA's moon mission. Draper built the Apollo guidance, navigation, and control system to operate semi-autonomously, providing autonomous control but with a human in the loop. Stemming from our early development of vehicles that required autonomous operation, we have developed vehicle systems that incorporate human-like intelligence and software. These autonomous vehicles span multiple domains including land, air, sea, and space. The type of autonomy employed by these systems varies according to the mission need. Timeliner, our scripted automation technology, has been deployed on the Orbital Express demonstration system and the International Space Station. On Orbital Express, a program designed to demonstrate a cost-effective method for autonomous satellite servicing, Draper's mission manager provided a novel approach to multiple levels of human control over the automated script execution. On ISS, Timeliner is aboard both the payload and the command and control MDMs. It is used to automate the ISS core and the ground procedures for the payload operations and integration center cadre. Our automation technologies have also been used in the commercial sector to automate power plant monitoring and telecom operations. Our intelligent autonomy technology is based on the human planning process. Its architecture, which utilizes a hierarchical decomposition of tasks, enables conceptualization and predictability into the task timeline for multi-level, closed-loop planning and control systems. Using this approach, a system can function completely autonomously or in collaboration with a human. Draper's decades of experience in developing intelligent underwater vehicles have resulted in our creation of an open, reusable architecture which separates the mission and domain-dependent aspects from the domain-independent portions of the technology, allowing for considerable extensibility for new capabilities such as sensors and mission activities. Over the last 6 years, Draper has been supporting NASA in the Autonomous Landing and Hazard Avoidance Technology program. The purpose of ALHAT is to develop the technology needed to enable precise planetary landing. Part of the challenge in this program is to use novel techniques and sensors to identify and avoid hazards while in the process of landing. More recently, Draper has been supporting terrestrial flight testing of the ALHAT system. The purpose of these flight tests was to demonstrate the landing sensor technology and the landing profile of the Draper-developed autonomy, guidance, navigation, and control system. For this test, ALHAT sensor and processing were flown by helicopter to simulate the dynamic response of a planetary landing vehicle. Draper has extensive experience developing dynamic mission management systems. An example is the Risk-Aware Mixed Initiative Dynamic Replanning System developed for ONR. RMDR provides mission planning, operator interface, and real-time replanning technology for monitoring and control of multiple heterogeneous autonomous vehicles with limited intermittent communication. JAGUAR, the Joint Air-Ground Operations Unified Adaptive Replanning System, supports operations with advanced automation. It reduces the effort required to complete initial planning and enables real-time replanning and thus can accommodate an increased ops tempo. The architecture was designed to adapt to new platforms, sensors, and tactics as necessary for each mission. The ability to represent tactics as models is a significant technological advance provided by JAGUAR. Key to many of the systems that Draper develops is the effectiveness of the human collaboration with the overall system. Draper's human system collaboration capability encompasses a set of technologies and methods applied to enable effective human interaction with complex dynamic systems based on the operational context and workflow, as well as the user's cognition. We do this by performing a detailed analysis of the operations, goals, and specific tasks the operator performs, which includes developing models of the user's tasks, cognitive processes, and workflow. In systems in which automation is applied to augment or replace human capabilities, such as in supervising autonomous vehicles, we perform analysis to decompose and allocate functions and specific tasks between humans and automation to exploit the strengths of both and mitigate the weaknesses. We apply techniques to quantify the physical and cognitive load imposed by an architecture as part of our analysis design approach to ensure achieving these objectives. We have recently applied these capabilities to develop intuitive mobile solutions for the Air Force and the Coast Guard to support enhanced situation awareness and extend the communication and collaboration abilities. TacDroid, developed on the Android operating system, is a solution for determining target location, target designation, and enhanced collaboration with the air assets. All interaction is through the map, building upon the JTAC's navigation expertise. Through simplified interaction mechanisms, the user can send a message, such as an air support request, by selecting a point on the map and then adding supplemental information. Draper is conducting fundamental research on spatial disorientation during spaceflight with collaborators at MIT's Manned Vehicle Lab. An example is the research we are conducting for NASA's National Space Biomedical Research Institute on characterizing sensorimotor challenges during lunar landing and the countermeasures such as additional displays that mitigate these challenges. Draper has developed flight software and mission planning tools to enable precise battlefield cargo delivery for the U.S. Army. Guided airdrop systems, like those shown here, deliver cargo using a steerable parachute canopy that is driven to the target by Draper's onboard guidance, navigation, and control software. Key to the AACUS system will be its ability to use ground features for navigation and obstacle avoidance. Draper has developed vision-aided navigation technology that has direct applicability to this problem. Extremely high-cost navigation systems can provide relatively stable position and orientation information for autonomous vehicles, but will eventually experience position drift and do not necessarily help avoid local obstacles. The NANO Air Vehicle program, sponsored by DARPA, called for a nano-sized aerial vehicle to be remotely flown by an untrained operator. Through joystick movements, the operator informs the vehicle where to fly, and the vehicle determines the necessary blade positions to accomplish the command. In order for the vehicle to determine its location and correct for position drift in the inertial sensors, Draper developed the vision-aided navigation system, which employs two cameras, one in the front of the vehicle and one on its side. This system identifies features in the environment which the algorithm uses to determine position and orientation. Highly agile maneuver capability will be necessary to allow AACUS-enabled vehicles to carry out demanding missions in potentially hostile environments. Traditional command generation and control methods are based on flight control around a vehicle's trim conditions and fail to leverage the full dynamic capability of the vehicle. In DARPA's software-enabled control program, Draper developed hybrid logic-based control methods to exploit more of the vehicle's reachable space. The hybrid logic controller serves as an outer control loop in the vehicle's autopilot flight control system. The hybrid logic method consists of an offline design phase, where the vehicle's dynamic model is analytically deconstructed into maneuver and trim libraries, and an onboard reconstruction phase, where those basis functions are spliced together to synthesize a dynamically feasible trajectory between waypoints meeting operational constraints. On the SEC program, using the Georgia Tech RMAX helicopter, Draper demonstrated rooftop-level flight and sniper avoidance using aggressive maneuvers. Draper participated in DARPA's Unmanned Combat Armed Rotorcraft program, providing mission planning methods including dynamic retasking and coordinated control of a hybrid fleet of VTOL aircraft consisting of manned and unmanned vehicles, supporting autonomous operations in battle space. Draper also provided the autonomous vehicle control capability for low-altitude terrain masking and avoidance flight in challenging terrain consisting of mountains, ravines, and dense canopies. Draper is looking forward to taking on the technical challenges AACUS presents. As you have seen, we have a lot of capabilities, components, and experience directly applicable to the AACUS program and mission, and we have a track record of successful autonomy demonstrations in many challenging environments. If you are interested in joining our team, please contact us. Thank you for your time.